Good morning. Hope your day is going well. I hope your weekend goes even better. Today what we're going to do is we're going to do some more exam review for next week's midterm exam. Monday, everybody in this class anyways, Monday at 1:10 we'll take the second midterm. The midterm will have 12 multiple choice questions, 4 short answer questions, about 90 minutes in length. When you come to the midterm, bring your calculator definitely, something to write with. QA1 lab would be cool. I'll give you a periodic table. You'll turn in the exam prep 2 worksheet, single page double-sided, question and answer, show your work how to go from the question to the answer. We'll do the QA3 lab afterwards, which is very similar to QA1. QA3 has a lot cooler colors, so colors always are kind of neat to me. QA3 has some really spectacular colors, definitely. But like QA1, try not to bring any open-toed shoes. Shorts are not the coolest, stuff like that. Bring your safety goggles. Never a dull moment. Questions? All right, so without further ado, let's get right into it. Start checking out some more stuff. We looked on Wednesday at lots of solubility, KSP kind of stuff, but there was one more kind of problem from chapter 14, which was important, chapter 15, excuse me, and that's on formation constants, all right? So one of these reactions up here shows the formation constant for this species right here, CrCN6 with a -3 charge. And see if you can remember which of those would be the correct expression for a KF expression, which would be the right equation for a KF. So think about this a little bit, we'll talk about it here. Okay, so these KFs are all formation constants. They're for the complex ions, which is something we'll talk about in the next chapter a little bit more. But anyway, if you have a KF expression, the important part is that the complex ion, which here is CrCN6 -3, it's going to be a product, all right? This is different from KSPs, where KSPs, whatever the KSP was for, that compound was a reactant, and the ions were the products. But for KFs, this crazy thing is the product. And then the reactants are just whatever you need to make it happen, all right? So in this case, whatever you need to make it happen, that would be 6 cyanides, and you'd also need a chromium +3. Now, every cyanide is -1, and there's 6 of them. So -6 +3, that's where the -3 part comes from. So in this case, answer E would be right, all right? You could make the complex ion from chromium 3 cyanide, it's true. However, a true formation constant, just the raw pieces, all right? You don't want to put any compounds in or something like that. So although this would be one way to make it, this would be the true KF expression. That makes sense. Questions at all? You can relate all equilibrium constants, KFs, KAs, KBs, etc., to delta G. So here we have a KSP value, and we'd like to know what the delta G value is. Now notice here that the units of the answers, the legitimate answers anyway, are all in kilojoules. So keep that in mind while you go through your problems. See if you can figure out what the answer is going to be. So. All right, so the way to relate an equilibrium constant K to delta G is this beast up here. Delta G equals minus RT natural log of K. Now R is 8.3145, the energy R I've been calling it. Temperature here, of course, is going to be Kelvin. So 25 Celsius would be 298 Kelvin. So in your calculator, go minus 8.3145 times 298 times the natural log of this number right here. And initially the number is thousands, all right? But if you divide by 1,000, you'll get an answer over here, which makes sense. But before we go there, K here is a number less than 1. Does that mean that it's product favored or reactant favored?
Reactant?
Reactant, right on. Reactant favored Ks mean you're going to easily see a solid here in this case, which is true. So if you have a reactant favored K, that means that it's not likely to go from reactants to products. So your delta G value in this case should be a positive number if you've done all the math right. So when you plug this in, if you forget that minus sign, which is very easy to do, sometimes you can rationalize what the actual answer will be. But it looks like people were taking care of business here. When you throw all this in, 34.8 comes out to be the answer. So a non-spontaneous delta G corresponds to a reactant favored K. It's all coming together. Questions except for why I'm so excited by that. I mean, anyway, good. All right, on to the next problem. Okay, so here comes the beasts. Balancing redox reactions. This is an example of taking permanganate and iodide and making manganese 4 oxide and iodine, excuse me. I'd like you to balance it, but I'd like you to balance it at a pH of 8.37. Now there's several different ways you can do this. You can go right ahead and start balancing in base with hydroxide and water, and that's fine. I would probably do this in acid first and then neutralize in base, which is longer, but that is a cool way to do it. So see if you can do this. We'll talk about it here in a little bit. Let's do it. Okay, so these kind of problems, first of all, recognize if it's an acid or base. And like we talked about this week, anytime your pH is under 7, it's going to be acidic. Anytime it's over 7, it's going to be basic. So any pH value over 7, that was when you'd use hydroxide and water. But if the pH was under 7, then you'd use H plus of water. So I find it a lot easier to do these reactions in acid first and then neutralize in base. However, if you can go direct into hydroxide and water, it does save you time. So find the method that works for you. There's no wrong answer. I'm going to try and show you both ways here if I can. So first of all, the answer was D, and I will just talk about that. But here's how I would do it if I was doing it in acid, okay? So in acid, what you'd want to do is you want to break up the reactions into half reactions. So the iodide and the iodine would be one half reaction, and the permanganate and the MnO2 would be the other one. All right, so you just put the species that are similar to each other together. Now this one is simple, all right? 2 atoms of iodide are needed because the iodine is a diatomic. You have 2 atoms. So you've got to make sure the atoms are balanced. So that's why we put the 2 right there. And then because there's 2 times -1, the whole reactant side is -2, but iodine doesn't have a charge. So to balance the charge, you add negative electrons. We're going to add 2 electrons to that side. Now there's -2 on the product side, -2 on the reactant side. The atoms balance, we're good to go. Questions on the iodine part? Okay. In acid, this one is the next one to tackle, and this is where, again, I'm pretending it's in acid, and I'll neutralize later. So in acid, I see there's 4 oxygens versus 2 oxygens. So I've got to add some oxygens. That's where the water kicks in. I'll add 2 waters to that side, but then by doing that, I have 4 hydrogens. So I can also add H plus if I'm doing it in acid. So those would be the balanced atoms. A manganese, 4 oxygens, and 4 hydrogens are on both sides. And then like the last one, I've got to neutralize, or I have to balance the charge, excuse me. The whole product side is neutral, but the +4 and the -1 from permanganate make an overall +3 charge. And again, MnO2 and water are neutral, so I've got to bring that +3 down to 0. I can do that by adding 3 negative electrons. And then you've got -3 from the electrons, a -1 from the permanganate, and a +4 there. So all of it goes to 0. Both sides are balanced. Woohoo! Questions on that? All right. Then you want to mix the reactions together, and you don't want to show electrons. That's really bad news in chemistry. So there's a 3 and a 2 right there. So that means what I need to do is I need to multiply by a common denominator. And usually just like 3 times 2 is 6. That's a good way to find it. 6 divided by 3, we're going to multiply the whole permanganate reaction through by 2. So you can see here I've got 2 MnO4s and 8 H plus, et cetera, all the way to. And I'm going to do something similar here, but I'm going to multiply this side by 3. So then I've got 6 iodides, 3 iodines, 6 electrons. Then you combine them all, the 6 electrons cancel out. This is the balanced reaction in acid, okay? It's not in base yet, but at least it's done in acid. Acids, once again, have H plus, and so we've got to get rid of that on the next step to figure that out. Questions on this part? Okay, now, and again, in my longer way of doing things, what I'm going to do is for every H plus I have, I'm going to add a hydroxide. But just like in math, if you add to one side, you've got to add to the other side. So I'm going to add 8 hydroxides to the reactant side and 8 hydroxides to the product side. Now, 8 hydroxides and 8 H plus will make 8 waters, all right? That's the neutralization part of all of this. So the 8 OH minus and the 8 H plus will combine to make 8 waters right there, but you have to add the hydroxides to that side as well. At this step, see if you've got water or hydroxide or something on both sides. In this case, as you can see, there's some water, so I'm going to subtract 4 waters from both sides. And this reaction now, this is the balanced reaction in base. There's no H plus going around. Hydroxide is cool in base. I've got water. Everything's good to go. Now, that's my longer way of doing it. So If you can do it straight with hydroxide and water, it is simpler. So I'm going to try here to do this. And I always get confused, and I'll talk about why I get confused. And you're hopefully smarter than me, and you can get around it. So like before, I'm going to balance the iodines by having a 2 right there. And like before, I'm going to add 2 electrons to make that balance. So there's no changes to that one because there was no H plus in hydroxide. But up here is where it gets tricky, all right? I've got to add some oxygen to the product side. Now, you want to add hydroxide to the side that needs oxygen. So the problem in my thinking always is I'm like, oh yeah, okay, I'll add 2 hydroxides. And that'll make the oxygens all balanced. But the problem is you can only add hydroxide and water. And water, as you know, comes in H2O. So almost inevitably, you end up using twice as much as you need. I don't know how else to explain it, but that's kind of what it feels like anyway. So I need to add now some water to this side to make it balanced out. Oh boy. Let's see, I think this is going to be 4, and then I've got 4, 5, 6, 4, 5, 6, 2, 2, 4. Yeah, so I've never understood this process, gang. I won't lie. Instructor Confessions 101. But anyway, I don't know why this 2-to-1 thing works, but it does, and it freaks me out. So that's why acid followed by base, that makes sense to me. However, if you can do it this way, that's great. And like I've said, always check yourself, and I'm going to check myself. 2 times 2, 4. 4 hydrogens, both sides. 4 plus 2 oxygens. 4 plus 2 oxygens, manganese. So it does balance out, and you can do it. And I bet a lot of you can. But for me, that's just never worked. It's always freaked me out. So, all right, Prophet back on. I think it fell off there. Questions? Okay, so once you have it balanced, then it's pretty chill. -1, -4. We need to add 3 electrons. We're going to multiply this all through by 2, like we did before, and this one by 3. And voila, we'll end up with the same thing at the end. All right? So, a couple of things to take away here. You can do it either way, all right? I really don't care which way you do it. This way is a little less work, but that 2-to-1 thing kind of freaks me out there, so it always messes with me. Check yourself at any stage, all right? And that's what I just did right now because I wasn't feeling very confident about it, all right? You can check the half reactions and the full reactions. And finally, if you've done the reactions right, electrons should be reactant on one half reaction, and electrons will be the product in the other. You've got something being reduced/oxidizing agent. You have something being oxidized/reducing agent. Questions on anything? All right. So any way you want to do these are fine. Check yourself at the end. You'll be good to go. Let's get out of here. Okay, so here are some reduction values. All of these have electrons as reactants, so they're being reduced. Aluminum 3 plus to aluminum, cerium 4 plus to cerium 3, etc., etc. And the question is here, what is the strongest reducing agent? Now, strength of things is usually seen as more positive, but you've got to think about what it means to be a reducing agent, okay? So think about this. We'll talk about it here in a little bit. See if you can figure out what this all means. For everyone that submitted an iClicker already, remember it's reducing agent. Good. Okay, so these values work really well if you're talking about oxidizing agent. An oxidizing agent is something that likes to be reduced. A reducing agent is something that likes to be oxidized. So in terms of oxidizing agent, i.e. something that's being reduced, cerium 4 plus loves to be reduced. The most biggest E value here, that's the one that's going to be really, really happy to be reduced / oxidizing agent. But this question isn't about oxidizing agent, it's about reducing agent. And a reducing agent is something that likes to be oxidized. So, for example, this reaction right here is a reduction. How would we turn it into an oxidation? Flip it, that's right. We would flip this reaction around. So aluminum would become the reactant, and these would both become products. What do you do to the sign of E when you flip it? Make it positive. Yep, that's right. Just change it from negative to positive. It's like Uno when they have the reverse card. Okay, Prof hat back on, that was silly. Anyway, so if you're going to talk about oxidations, you're going to use the opposite of all these values. So cerium 3 plus would hate to become cerium 4 plus. It would have a negative 1.61 volts as an example. On the other hand, aluminum would love to become aluminum 3 plus and 3 electrons because its E value would be positive 1.66 volts. So the strongest reducing agent is the one that wants to be oxidized the most, and it's going to be aluminum, all right? Aluminum 3 plus would, in this case, want to be reduced. Well, not really, because it has such a bad E value. But aluminum would love to be oxidized because it has the most powerful, positive, if you will, E value there. So just remember, those agents are the opposite, all right? It's always the opposite of what you might think they are, so. Any questions on that? So these kind of questions are the crux a lot of times of these kind of problems. Will something oxidize, reduce something else? So here we've got tin, and we're just asking, will tin reduce silver plus to silver? So using these values right here, see if you can say yes or no. It's not answer C, you can probably imagine. But anyway, see if you can figure out which of those would be the best answer. Okay, the answers are evenly split between yes and no. So let's figure this out and see if this is going to happen or not. When you see a problem like this, I think it's really important to remember what the reactants are and what the products are. So in this question, it's saying if you put tin solid, tin metal with silver plus, will it make silver? So in the half reaction, which I started up here then, tin is going to be one of the reactants. Silver plus is going to be one of the reactants. And the question is, will it make silver? So I'll put regular silver there. And you can probably see from this reaction then that tin 2 plus is going to be the other reaction. So in this problem, you want to figure out the E value of the overall reaction. Positive E's correspond to negative delta G's. So positive E's means it will occur, and negative E's means it won't occur. Now, these are reductions. We're going to have to flip one, all right? And you can probably see here that tin, we need that as a reactant. We don't want it as a product, all right? So we're going to change the sign of the E. We're going to flip this reaction around. So tin becomes a reactant. That'll be positive 0.14 volts. But we're going to leave the silver alone because silver plus is already a reactant, and that's where we want it. So positive 0.14 plus positive 0.80 comes out to be positive 0.94. This is going to happen. E values that are positive are the ones that are product favored, and they're going to go down. All right. If this would have been a negative 0.94, then we would have said, no, not going to happen. But in this case, yep, comes out to be positive. We're good to go. Any questions? All right. This question, we have a redox reaction. It's chlorine and iodide making chloride and iodine. And the E value here is given positive 0.825. And what I'd like you to do is calculate the equilibrium constant K for this reaction at 25 Celsius. So see if you can figure out what that is. Use delta G equals minus NFE. You can also use delta G equals minus RT natural log of K that we used earlier. See if you can figure out. We'll talk about it in a little bit. Okay, so delta G equals minus NFE. Delta G also equals minus RT natural log of K. So if you let those equal each other, because it's all delta G, then minus NFE equals minus RT ln K, cancel the negatives because they're just annoying, and you can then solve for K. So let's go through here and figure out what these different values are. N is the mole of electrons, and you can look at chlorine or iodine. If you look at chlorine, Cl2 to 2Cl minus, the atoms are balanced, and to balance the charge, you would add 2 electrons to chlorine. So 2 negative electrons plus Cl2 would equal 2Cl minus. That's how you can figure out that N here is 2. And you don't like chlorine, you want to use iodine, fantastic. 2 -1 iodides to I2, which is neutral, you would need 2 electrons as products. So through either reactants or products, N is going to be 2. And then the Faraday constant, 96,485. The E value is that 0.825. R, 8.3145. Temperature here is 298 Kelvin. So the only thing then you don't know is K. So you would essentially take the anti-natural log E to NFE over RT to solve this beast. Now sometimes the sticks get crazy, but if you pick the number which is closest, that's fine too. It comes out to be very, very product favorite. Now one thing in your advantage here is that positive E's are spontaneous, negative delta G's. And negative delta G's correspond to K's which are greater than 1. So as long as you get a K that's greater than 1, that at least makes sense for the math. So A and D are both numbers less than 1, they wouldn't flow. That's not an equilibrium constant at all. K has to be a positive number. Any questions on any of that? Okay. Here is a voltaic cell that's created using this information below. And it's in Alaska, so supposedly it's cold outside. I don't know, it's like some cold place. What we can do is with this information, calculate the cell potential. Now notice here, there's a lot of things that are a little strange. And strange to me means not standard states. So you see the temperature is not 25 Celsius. Your concentrations are not 1 mole per liter. So this is where you're going to have the Nernst equation. E equals E0 minus RT over NF natural log of Q. So see if you can use this information to first calculate what the cell potential is going to be. okay? And in this problem, the cell potential, because it's voltaic, you have to end up with a positive voltage, all right? Voltaic and galvanic means it's a battery that works. So figure out what the positive voltage is going to be here. And from there, you can plug these other pieces in here and find Q, products over reactants. See what you can do. We'll talk about it here in a moment. Okay, so on a problem like this, voltaic or galvanic means product favored. That means get a positive voltage out of these two numbers somehow, all right? And the only way, you have to flip one because these are both reductions, so one of them has to be an oxidation. To get a positive number, flip the aluminum, all right? And aluminum is the source of the electrons. Remember, electrons always flow left to right in these things. So basically all these things are just saying flip minus 1.66. So 1.66 minus 0.25, that'll become, I think, positive 1.41 volts. That's the E cell under standard conditions. But darn it, we're not using standard conditions. So R, 8.3145, temperature, 5 plus 273 would be about 278 or so. N is a little trickier here. Notice how there's 3 electrons and 2 electrons. So when the electrons are canceled, you've got to make sure they all go away. So we would go 3 times 2 or 6. N here is going to be 6. All right, to make all the electrons go away, this is a 6 electron transfer. And then F here is the Faraday constant, 96,485. Now Q is going to be products over reactants, all right? And remember, we're flipping this one around, so aluminum 3 plus becomes a product, and nickel 2 plus is still a reactant. So products would be this number squared, because there's going to be 2 of them when you balance it, divided by the nickel 2 plus on the bottom to the 3rd power. So a lot of weird parts right here, but here's the overall reaction with the overall E naught, 1.41 volts. And you want to basically find how the non-standard conditions change it. So RT over NF, you can see all these different values pop in. Products are aluminum 3 plus squared over nickel 2 plus cubed. We don't put any solids in equilibrium constants. So if you throw this all in together, 1.46 volts. A little bit more product favored under these conditions than it would be normally, which is kind of a cool thing if you want to supercharge it or whatever. Any questions? Okay. I'm just going to talk about this one because I don't have that much time left. But this is a quantitative electrochemistry, which means you either start with amount and go to time, or you go with time and go to amount. So in this case, we're starting with this many moles of this gold 3 plus, and it says how long time is it going to take. 3 moles of electrons are needed to make gold 3 plus go to gold. So the first thing you do is multiply moles of gold 3 plus by 3. That would make the gold 3 plus go to regular gold. And then 96,485, that's the coulombs per mole of electrons. So if you turn the moles of electrons into coulombs, amps means coulombs per second, so you'll divide by that. That'll tell you how many seconds there are, and you should be good to go. So here's the math. Moles of gold 3 plus. You need 3 moles of electrons to turn gold 3 plus into gold. Multiply by Faraday, divide by the amperage, will give you the second value, 1450 seconds. Okay. Questions? Any of that? Fantastic. All right, that's it for the exam review. On Monday, we will start a new chapter, which won't be part of the midterm, but it's kind of cool stuff, and my bias down. Thank you for being here. Have a great weekend.